We are covering the work-energy theorem and the principle of conservation of energy, a critical topic for the dynamics section of the Fundamentals of Engineering exam. These concepts allow you to solve problems involving forces, velocities, and displacements without needing to calculate acceleration or time, which is a huge advantage. You'll find the core equations in the dynamics section of your NCEES FE reference handbook under the principle of work and energy. Heading: The fundamental relationship is the work-energy theorem, which states that the net work done on an object equals its change in kinetic energy. The formula is W net equals delta KE, where kinetic energy is 1/2 mv squared. Work itself is calculated as the force times the distance, multiplied by the cosine of the angle between the force and displacement vectors. When we include potential energy, we can expand this into the full conservation of energy principle. For a system with no non-conservative forces like friction, the initial kinetic plus potential energy equals the final kinetic plus potential energy. Potential energy on the exam primarily comes in two forms: gravitational, which is mgh, and elastic from a spring, which is 1/2 kx squared. Now, let's consider a classic FE exam problem. A 20-kilogram block is released from rest at the top of a 10-meter-long ramp inclined at 30 degrees. The coefficient of kinetic friction between the block and the ramp is 0.2. The question asks for the speed of the block at the bottom of the ramp. The first step is to apply the expanded conservation of energy equation. Initial kinetic energy plus initial potential energy plus work done by other forces equals final kinetic energy plus final potential energy. A common exam trap is forgetting to define a datum for potential energy. Let's set the potential energy to 0 at the bottom of the ramp. At the top, state 1. The block is at rest, so its initial kinetic energy is 0. Its initial potential energy is mgh, where h is the vertical height, calculated as 10 meters times the sine of 30 degrees, which is 5 meters. At the bottom, state 2. Its final potential energy is 0 because it's at our datum. The final kinetic energy is 1/2 mv final squared. And that final velocity is our target. The work done by other forces term here is the work done by friction, which is a non-conservative force that removes energy from the system. This is the biggest trap. The work done by friction is always negative. The force of friction is the coefficient of kinetic friction, μk, times the normal force. On an incline, the normal force is not just ng, it's ng times the cosine of the angle. So, the work done by friction is negative μk times mg cosine theta times the distance d. Plugging in our numbers, we solve for the final velocity. A key mental shortcut to remember is PEK in equals PEK out plus losses. This helps you remember to account for potential energy, kinetic energy, and any energy lost, primarily to friction. Always double-check your units and make sure your signs are correct, especially for the work done by friction. For free practice questions, AI-powered explanations, and more exam prep tools, visit openexamprep.com. That's openexamprep, all one word, .com.